All right, so let's talk about scaling and in particular LSA. Well, we'll talk about a few different aspects of LSA and what it means in terms of scaling. There are some new developments coming with CDM that are interesting from an LSA perspective. And there are a few different things to think about when you design your service for scaling in this particular way. So traditionally, we've had device clusters for scaling the number of devices. And that was all they really, well, they were good for a few things. But the driver for creating them was that we wanted to manage more devices than could be easily managed by a single NSO instance. So we created these what we call device clusters, and they were essentially invisible to the service code, which was really nice. So you could have the same service code that worked on local devices or remote devices. And you could scale your network of managed devices to a really large number. But they had some problems. So they were really nice to use, except they were extremely slow. We are talking about a slowdown of the scale of five times slower maybe, or even worse. And that was after we had optimized the performance of the cluster. So they give you scalability and they give you a really nice single pane of glass view of your entire network. You get the CLI that covers your entire network, even if it's distributed across multiple NSO nodes. So in response to the performance issues with the original device clustering solution, we came up with another design when we hit this performance wall, if you like, and we had exhausted our abilities to optimize the device cluster. And that's what we call layered service architecture. And what that is essentially is the upper node, you have multiple layers, the upper NSO node treats the lower NSO nodes just as any devices. So conceptually, you can view the upper node as being just an independent NSO node that manages a bunch of devices, and those devices happens to be other NSO nodes. It's not uncommon for NSO to manage EMSs that themselves manage the devices. And in this case, we made this into a general sort of solution. And the advantage of that is that the upper node doesn't have to know about any of the devices. It doesn't have to read all the device configuration through the lower nodes. So that makes it a lot faster. The only thing that needs to go between the upper node and the lower node, or the lower layer, are the actual minimal set of parameters for a specific service. So the way to think about this is as an abstraction layer, if you like. So on the upper node, you have your higher service product abstractions, whereas on the lower nodes, you would have your lower resource-facing services. And with this design, you get higher throughput. You get much better performance or response time compared to the other clustering solution. You still get, in most cases, worse response time than having a single node. So if you have a single node that is, in most cases, what gives you best performance, especially if you don't have a huge device network. But this gives you better scalability, and reliability is not really impacted in an interesting way. You could argue that it gets better, but also worse. You have more points of failure, but you have, as I get to, you have a better situation because you can upgrade the system in a bit more, in an easier way. So if we compare these two cluster solutions, it's essentially what I've said. You from an LSA cluster, you lose the knowledge of seeing all the device nodes. So you don't have this single pane of glass view anymore. I'll show you in a demo that you can have some of that, but it's not as nice as in a device cluster. You also have to tailor your services specifically for this scaling model. So it's not as seamless as with the device clusters. You do have some communication penalty, but it's not as large as for device clusters. You have a much easier upgrade scenario. So when you have a device cluster, you have to more or less upgrade everything at the same time. Whereas with an LSA cluster, since what is exposed by the lower layer are only the service models, the actual devices themselves and the service logic residing on the lower node is not exposed to the northbound. So you can upgrade the lower node as long as you keep the same northbound interface. Your service interface is backward. It doesn't necessarily have to be the same, but it can be. It must be backwards compatible. In that case, you can upgrade your lower node without upgrading your upper node, and vice versa. You can upgrade the upper node without necessarily touching the lower node, so you can do it in a rolling manner. And also, in device clusters, all your service code was executed on the upper node. So that had to essentially deal with all service code execution in the entire network. That's single node. Whereas in LSA cluster, you can push down a lot of the create code or service logic to the lower layers, which gives you parallelism. So you can also scale the computation logic that you have in your management network. Right. So LSA gives you scalability in two different ways, or maybe three, you could argue. There are many different other aspects of scalability and performance, but this is what you get with LSA. You get number of devices, but also you get parallel execution. So you can execute your service code, and that means both running the actual service create code, but also managing the diff set. So if you have large sets of change sets associated with the service, it's much better to have them parallelized on your lower nodes than actually having to have them in a single place on your upper node. And calculating those minimal diffs to send out to the device can be quite heavy, and that can also be parallelized if it's pushed down to the lower layer. And also the device communication get parallelized. So if you have, even on a single node, you can do, say, 100 concurrent communications, but you may still be resource bound by the actual communication. So suppose you have a setup, a 2-layer NSO LSA setup. You can now scale this. Of course, in the lower layer, you can just add new nodes, but at some point you want to extend the lower layer. But also, so then you would add a new lower NSO node to your network, and you add new devices there. Or you can make it into a 3 or 4 layer network if you want. There's nothing particular about having just 2 layers, even if that in most cases is enough. But you can, in theory, have multiple layers. And there are cases where that makes sense for architectural reasons. So, for example, you may want to have one lower NSO node per data center and then have one global upper NSO node to orchestrate among these data centers. And in the same way, you may want to split your service logic on different nodes for business reasons. There might be different parts of your business that feel responsible for different parts of the network. And for that reason, you may want to actually give operational responsibility for different parts of both your devices and also your business logic. And in a sense, you can view the upper node as a load balancer among the lower nodes. So in the ideal world, you would do some minimal resource orchestration on the upper node and then push as much heavy work as you can to the lower layers and get as much parallelism out of that or use of the CPUs. And as I mentioned, maintainability becomes better with LSA. You can upgrade the lower nodes. You don't have to upgrade all of them at the same time. You can even have different release cycles for the software running on those, for the service logic running on those lower nodes, and with the upper nodes for that matter. Okay, so what does it mean to run LSA? What is the impact for your service design or architecture? Well, with device clusters, you didn't really have to care. Some devices were mounted locally and some remotely. You just run your logic, applied your templates as if they were local. But in this case, when you're using LSA, you have to think about it a bit. In a way, your typical service design or system design is fairly well suited to LSA. And the way to think about it is, when you have a service, you typically divide it into stacked services, where the lower layers are closer to the device and the upper layers are sort of closer to the products or customer-facing services that you have. And at some point, if you're careful with your service design, you don't jump across layers. You don't have an upper service look directly into the content of a lower service. So if you try to carefully follow this layering scheme, it will be much easier to, at some point, move parts of the lower stack into a lower NSO layer as well. You have to think a bit carefully about how you do orchestration. So even if you have on the lower level layer, you could do resource allocation locally. You really have to sometimes move it up into a higher layer just because you're not really allowed to log into other services at the same layer or from the top down into a lower service. So if you have allocation of an IP address that you want to use in multiple places, and a higher layer is not really allowed to inspect the lower service to see what IP address it allocated, for example. So you have to do your resource allocation and your coordination at the upper layer. But it really boils down to having a nice, clean design in most cases. So that's not really a bad idea anyway. So on a single node, your design may look something like this. You have a CFS at the top and stacked services below it that eventually boils down to something that you apply to a template. Typically some templates that you apply to a device, that is. And when you move this into an LSA design, what you do is you decide where to split it up into multiple nodes. And you have to you have to modify the code a bit, but hopefully your design can be essentially the same as your single node design. It's possible to create services that allows you to have a mix of locally mounted nodes that you manage with the service, and also have remote nodes that are managed on a lower layer LSA node. I know that the team in San Jose have designed some of our core function packs to work like that. That you can have local nodes if you're running the service pack on just one NSO instance, and then gradually migrate to an LSA design where you have some of the nodes running on an LSA, a lower LSA node. And in some cases, it might be better to actually add an upper layer instead of adding a lower layer. So if you have a local node that runs service or your services, when you scale it, it might make sense to add a top layer that sort of load balances towards your lower existing node, and then you can add another sort of sister node or sibling node to that existing NSO node, and those two then becomes lower LSA nodes. You should, however, be aware that error recovery becomes a bit more complicated. If you have a single node, it's fairly easy to, well, it may not even be easy, but at least it's manageable to deal with errors when you have when your service fails for some reason. A device is broken, or a link is broken, or your service logic is broken, or whatever. But if you have multiple layers, it may not be as easy. You may have to jump into the lower node to fix something there instead of having to be able to just do the fixing on the upper node. We have added a bunch of helper tools to make this easier, but still, I think there is some added complexity there. Also, if you have reactive fastmap services, that is, services that react to some external event before they can proceed. So a typical example, or a couple of typical examples, are starting a virtual machine. So if you have a service that, as part of the service provisioning logic, it starts a virtual firewall, for example, and then starts orchestrating traffic towards that virtual device. You get a state in your service, and that state sort of progresses, it's sort of state convergence toward the final goal of everything being up and running. But if you split that across multiple layers, things get a bit more complicated. Typically, if you run it on a single node, you can have event notifications, you can have kickers that sort of notify your parent service that now is my sub-service ready. Say the sub-service is responsible for starting the virtual machine and putting it into an operational state. And then it will notify through a kicker the parent service saying that now it's ready, you can configure it. So if you have split that into two different layers, then the notification becomes a bit more complicated. So it's really fine from an abstraction layer for the upper service to just tell the lower service to start a firewall and not really have to care about it. The lower node can do all the heavy lifting and bring it up and everything. But once it's done, it needs to notify the upper service that, hey, it's time to progress the service or proceed. And in our current implementation, what is required is for the lower node to implement a new custom notification event or notification type. It needs to send that whenever the service is ready, and the upper layer also needs to somehow receive this custom event and react to it. And similarly, when it provisions the service, it needs to provision it using a namespace that is different from the one used on the upper node. And it actually all boils down to namespace clashes, because in NSO, prior to CDM that John talked about, we can't have the same namespace. So if a lower LSA node has the same namespace as an upper LSA node, they crash. They can't talk to each other. That namespace can't be used by the upper node because it has it itself as a northbound interface. So what we really would like to do is for the lower node to just be able to send an ordinary notification, a kicker notification, in that namespace, and have the upper node receive that. But currently it can't. So we have to write special code to work around that. In 5.0, that would actually all go away. So then in 5.0, this becomes much easier. You can, from the upper node, very similarly to what you do in the local node where you create a notification kicker to wait for something to be ready, you can do that across this LSA barrier, if you like. So you can, from the upper node, just create a kicker that looks for some state to change on the low node and then subscribe to the notification that the low node sends when that event happens. And also you can read states and plan data from the lower node. And not only that, one issue with using LSA is that it becomes trickier to manage devices. You have to add the device locally on the lower node. So you can't just manage everything from your top node. If in a device cluster you have just one place where you can manage all the devices, you can add them to lower device cluster nodes. But in LSA, the upper layer doesn't really see the devices on the lower node. So we have had, I know that some developers wrote their own packages for adding nodes on the lower layer, LSA layers, which is very useful, but it's a bit cumbersome. And you don't only have to add, I mean, you have to cater for a bunch of things. It's not just adding the node in a device in the device tree. You have to add authentication groups. You have to have actions for syncing and for reading SSH keys and a whole bunch of things that comes along with that. But with CDM in 5.0, since we are no longer restricted to or limited by not having access to the namespace of the lower node, we can actually directly manage the device set on the lower LSA node from the upper one. It's the same problem as in 4.0. It's the same problem as before. You have the NSO namespace or NCS namespace actually on the lower LSA node, and you have it on the upper one, which means that they can't talk. They can't communicate over make changes in NCS namespace, but with CDM they can. So I'll show that in a demo towards the end here. So another reflection or another ask we got when we started to push LSA as a scaling solution was that some customers or some projects wanted to scale even easier. So with LSA, as I've presented it, when you add a new device, you either add it on an existing lower node or you create a new lower node and add the device there. But it's not really easy to move devices between different lower LSA nodes. It's quite hard. You can, in theory, you can undeploy the service on the lower node, undeploy it on the upper node, and then redeploy it on a new node, changing the dispatch table. But it's quite cumbersome. So we got an ask for making this easier to move nodes between or devices between lower nodes, I'd say. So you can load balance devices on the lowest LSA layer, and that would make it easier to expand. So if you have an LSA cluster that has grown and you have filled up your lower LSA nodes and you want to add more LSA nodes, what you can do is add another node and start adding devices there. But what if your services grow and takes up more resources, or the configurations grow on your existing devices? Then you end up in a constrained environment where your existing node sort of gets filled up. You can potentially not do what you want to do. So in that case, it would be nice to be able to load balance them, add an other lower layer, and then just divide the nodes among them. And we came up with a solution for that, that makes that possible. And the observation is that what makes it difficult to move a device from one node to another one is that there are potentially lots of different services touching the same device in sort of an uncontrolled way. But what if we had just the device configuration and services touching a single device? Then we could fairly easily package that up as a single configuration file and move that to another node and install it there. And then we just have to update whoever created those services to point to the new node instead. So we came up with a design where we have just the ordinary device configurations. Oops, it is. And as you see here, what we have that you typically don't look at when you look at device configurations, because it's not there by default, but you have to use a pipe flag, is that everything that a service has touched in your device configuration has a back pointer pointing to the service that created that owns that piece of configuration on the device, and it has a ref count. So you can see that if you do show configuration bar display metadata, service metadata, you'll see these ref counts and back pointers. And if we place all resource-facing services associated with a device under a certain point, so in this case we have the device called X0, and all resource-facing services are placed in that list instance. It means that to move the device, all we have to do is package up the device configuration under device X0 and the RFS instances under the RFS device X0. And then we go to go. We can take that, install it on some other lower NSO node, and be happy. So suppose it looks something like this. We have two existing nodes. We have a dispatch table that's used by the service logic on the upper LSA node, saying that device D1 resides on node 1, D2 on node 1, D3 on node 1, and D4 on node 2. Now, to move a device from N1 to N2, what we do is we take a partial lock on the upper node for N1, which prevents anyone from provisioning new services on that particular lower NSO node. Then we, from the upper layer, extract the device configuration and RFS configuration for that device we want to move, say D3, on lower LSA node N1. We install it through another action on lower LSA node 2. We update the device map saying that D3 now lives on N2. And up here on the upper LSA node, there are services that have created these resource-facing services on the device. They need to now be updated to point to the new location for that device. But as you saw on the other slide here, we have back pointers, and not only for the device configuration, but also for any other configuration. So we have full control of who has created, which service has references to this device on the upper layer. So we do a local redeploy on just those services, commit them without pushing anything to the network, and then we do a compare config of the two lower nodes, and that is just to bring the upper node into. It has already seen all the changes, but we want to bring them in sync. So with that operation, we have sort of moved the device, and this is automated as an action in example. There is an example that comes with NSO called example 24, laid service architecture, under the getting started with NSO, developing with NSO, or something like that. Now, it becomes a bit tricky if you're not happy with that. Suppose you still want this kind of scaling behavior. You think that it's nice to be able to load balance your devices, but you have reactive fastmap services. And then we can't really, well, we don't have a ready-made solution for you, but it's still possible to do. The problem here is that not only do you have to move the service and the device configuration, you also have to move the RFM state and also everything that triggers that state. So that's really hard. So if you, for example, if your service allocates an IP address, asks an IPAM system for an IP address, gets that, then proceeds to configure something locally. Now, if you move that, say you move it in the middle of the process of allocating the IP address, the answer has to go to the other node where it has moved to. It can't go to the first node anymore. Or if you have an event listener listening to some event from the network, say that a link has come up or something, that listener needs to move also to the new node. So you get a more complicated situation. But if you have a service that you know intimately, that you have developed yourself, you probably know all about these constraints, and then you can create the necessary extraction code for moving that service. So our team in San Jose have modified one of our core function packs as some sort of an experimental exercise for this. So Krunal Patel has taken the NFVO package and sort of tried to isolate everything that has to do with the state of creating a virtual machine on a vBranch device. And when you move the management of that vBranch device, you also need to move the virtual device that has been created on that device, and also all the netconf notifications, all the events that have already been processed that came from that device has to be moved. But it's certainly doable, and I have a demo. We'll see if we have time for that. But if you have a specific use case, you can actually do it, and it's not really hard. But you need to know what you're doing. That's what I'm saying. And there is some new features we had to add to NSO to make this possible. And one is to a MAPI option for when you read the configuration, extract the configuration, you can now give it an option saying, I want everything, operation and configuration data that is stored in CDB. And then you get that as a text file, and you can move it and install it on another node. Now, another aspect of this is HA. So if you have an LSA set up, what you really have in a real network are HA pairs for all of these nodes, right? So you have at least two copies on the upper node and at least 2 instances on the lower layers. And you replicate data between these. And this is the fastest and most reliable way to do it. But in some situations, you have a setup where you're willing to take some risk, or maybe not so much take some risk as dealing with a slightly more complicated potential failure situation. And what you can do then, and also it depends on your performance requirements, because this solution is a bit slower, but it's easier in other ways. And the observation here is that if it's so easy to move a device between different nodes, you can extract everything that has to do with the device. What if you also store that in a database? As soon as you modify anything, you store a copy of that configuration in a database. That means that when you move the device, you don't have to actually have access to the original node if you can just as well read it from the database. So you don't actually need necessarily HA pairs. So if one of these, well, you need it if you don't want to disrupt execute or manageability of your network. But if you don't necessarily need it if it's okay that it takes some small time to move a device. Because then you can, if this, say the L1 goes down, then you can reinstall those devices from the database into L2. You don't have to read the device configuration from L1 from the source node, but instead you can read it from the database. So it's potentially more convenient HA setup, but it has some drawbacks. It's potentially less secure. If you're unlucky, you can lose some changes. So if you commit something and then it crashes on L1, you don't have time to write the new configuration to the database. Then you may end up in a situation where you're losing some data. You still have the data. I mean, the real truth of the device is the device itself. You can do sync from, but still. Also, you lose some speed because in every transaction you will write to the device, but also copy the data to the external database. And you do lose some failover time, since it's easier to fail over to another up and running node than to move the devices. Okay, so let's look at some examples. So I don't know if you have looked at example 24. It's been, I think it was included in the last release, but it was after last Developer Days, at least. Oh, what happened? So the setup is as follows, the demo setup. There is an upper node and there are 3 lower nodes. They have 6 devices, all connected, 3 connected to the first lower node and 3 connected to the second lower node. There is a database, which is actually just a directory where the configurations are stored. And there is an empty lower LSA node. Let's see. Here it is. So we start some devices. We see that on the upper node we have just three devices, which are the lower layer nodes. We have a dispatch map. Maybe we could instead. So we have X1 connected to lower LSA node 1 and so on. These guys. So to make this a bit more interesting, we create a service, which is just a dummy VLAN service. What it will do is create some configuration on X1. And in this case, it won't create the configuration itself directly. Instead, it will create a resource-facing service that in turn on lower LSA node 1 will create the actual device configuration. And on lower LSA node 2, it will create some configuration on device X5. And this is the actual service instance that we are creating. You can also, if you, I don't know if you've seen this, but if you just do dry run, you will also actually see what happens on the lower node. So on lower node NSO 1, you'd see that we'll create this instance, which will in turn expand to this configuration on the device. So you do get some visibility in what goes on the lower node. So it's not completely hidden from you. But that's because we added support for it, specifically in this LSA case. So we commit that. And now what we have is so now we have a service running on, or configured at least on X0 on lower LSO node 1. We want to move that device to lower LSO node 2. And that can now be done with this action from the top node. So if we now look at the dispatch map, we'll see that X0 has been moved to lower LSO node 2. And we can also look at the modifications of the service. We can see that previously the resource-facing service was created on LSO node 1 for X0. Now they are both residing on LSO node 2. So everything has been moved and the service references on the upper node has been updated. So that's sort of nice. You can move devices. What you can also do are things like you can request a rebalancing of your lower layer. So if you just dry run it, what will happen when I run this is that device number 4 will be moved from low layer 2 to low layer 3, and also device 5 will be moved to low layer 3. So we try to move the minimal number of devices, or the minimum moves. But what you can also do is things like this. You can say that I want to rebalance my network, but I want just these nodes to be balanced. So you don't necessarily have to rebalance your entire lower layer. You can just do the ones that you're interested in. So in this case, if we run this, if we now look at the dispatch table, we'll see that I just dry run it. We look at it first. So now we load balanced between these two nodes. So they should have an equal number and they have one each, whereas number 2 has all of them. So we can just do general load balancing, and now they are evenly distributed along the 3 nodes. Another interesting thing that you could potentially do is an action that we wrote for evacuating every device from a lower NSO node. So if you want to shrink your lower layer, you want to remove every device that's on that lower NSO node, or if you want to do some maintenance to it. So you can, in this case, I'm removing all devices from NSO node 2, and then they will be balanced among the other NSO nodes. Yeah. So that's pretty much what you get there. let's instead have a look at CDM. So this isn't really in production yet, so I'm running this from one of the developer branches, build of NSO from those branches. But this was actually not intended. The reason we developed CDM, but it was one very fortunate side effect that we're really happy about, making LSA better. So what all this comes from is a package called LSA Common. So as part of the CDM build, we now have an option for creating an LSA Common package that will include the data models in the proper NED IDs for managing the lower LSA nodes. And now we can do things like so I can inspect the device tree. I can't see the actual configuration, and we don't want that, because then we would be essentially back to the device cluster situation where we can have access to all the device configuration, and we really want to avoid that. But now from this upper node, I can add new devices. I can modify auth groups. I can do essentially what is needed. I can also run actions on a device. So for example, I can do x3 sync from on that lower node. So this is really nice from management perspective. All right, so that's all I have to show. And now Advanced Services have some actual live use cases of LSA to talk about.